All right, so let's resume. It is my great pleasure to introduce Professor Edgard Almeida Pimentel from Universidade Federal de São Carlos. He will be talking about W2P estimates for fully nonlinear elliptic equations and asymptotic approach. Please, Edgard.
Thank you, Diego. Thank you, Ricardo, for your kind invitation for me to talk in this session. And it's a pleasure for me, and it's an honor to be here at the Brazilian Colóquio. And for that, I thanks also the scientific committee and the organizing committee of this event. Okay. So today I'm talking about W2P estimates for fully nonlinear elliptic equations and asymptotic approach. This is a joint work with Professor Eduardo Teixeira from Universidade Federal do Ceará, currently visiting São Carlos, ICMC. And the outline for today is the following. I'll start with a brief introduction, then I'll talk about geometric tangential analysis. This is at the core of our argument, and for this reason I expect to spend certain amount of time talking about geometric tangential analysis and geometric tangential methods. Then I'll proceed by presenting our main result. There's namely W2P a priori estimates for solutions of fully nonlinear equations, uniformly elliptic fully nonlinear equations. Show you the main ideas of the proof. This will be a really brief discussion, and then conclude by presenting some of the consequences of our results to the general theory of fully nonlinear uniformly elliptic equations. In particular, I will talk about the extension of our result to the case of variable coefficients, also about regularity in Bml spaces, and finally about the density of W2P solutions in the class of continuous viscosity solutions. Personally, this last stop is the one I happen to find the most beautiful among the three. Okay, so let me start talking about the problem we are considering today. So you're studying an equation in the unit ball f d2u equals f, where f is a fully nonlinear elliptic operator, which means that there are constants, lambda and capital lambda, such that for every matrix in the space of symmetric matrix, in the space of d-dimensional symmetric matrix, we have these two inequalities for any non-negative matrix n. Okay. We also assume the source term to be continuous in the unit ball. Right. This assumption too here is understood in accordance to the theory of continuous viscosity solutions, right? Under weaker formulations, under formulations in LP viscosity solutions, we could work under integrability conditions on f. But for now, we'll suppose f to be continuous. Okay, so this is the problem we're interested, and we are interested in the regularity theory for solutions of this equation, right? So this is a topic that has been widely studied in the literature, and I'll continue by discussing with you a few breakthrough results that appeared in the course of the last 30 years. Okay, so the first very, very important result that actually unlocks regularity theory for this class of problems is due to Krylov and Safonov in two papers in the turn of the 70s to the 80s. And what these authors prove is a Harnack inequality for linear elliptic equations in non-divergence form. Right? Through a linearization argument, it is possible to prove that solutions to the homogeneous fully nonlinear equation are actually a priori C1 alpha for some alpha is strictly between 0 and 1 that is unknown. Right? So this is in the turn of the 70s to the 80s. A few years later, Craig Evans and Krylov, independently under the assumption of convexity on the operator f, managed to establish that solutions to the homogeneous equations are indeed C2 alpha, again for some alpha between 0 and 1 that is unknown. Right? This result is important because it unlocks somehow a theory of classical solutions for this equation. So this is, at some point, to some extent, these results regularity in holder spaces. Right? Regularity for this problem in Sobolev spaces, and I mean specifically W2P regularity, is studied for the first time by Luis Caffarelli in 1989 in a seminal paper in which Caffarelli studies the equation non-homogeneous in the presence of variable coefficients, right, and establishes W2P regularity and W2P a priori estimates for the solutions of this problem under certain assumptions, two of which are central. The first one is convexity or concavity with respect to M for the operator F. And there's another assumption that relates the fixed coefficient operator F of x naught for some x naught fixed in the unit ball, and the operator with variable coefficients. They somehow must be close. Right? This proximity measured is defined in terms of the oscillation. This quantity will be the oscillation, will be the supremum. And the assumption, Caffarelli's assumption here, is that this quantity is actually in LP and is small in an LP sense. Right? Okay, so under these two assumptions, Caffarelli in 1989 managed to prove W2P regularity and W2P estimates for solutions of this problem. Okay, so it seems to be, if we were in the 80s, it seems to be a very promising research program, and we would expect to answer questions like, is it possible to obtain a general regularity theory for equations of this form? Or in other words, can we generalize to some extent? Is it possible to obtain, for instance, W2P regularity for any fully nonlinear equation? Right? This kind of question, which is pretty natural given this corpus of results, remained open for quite a while, and very recently they were set in the negative. And they were set in the negative in a series of papers by Nadirashvili and Vladut, in which a series of counterexamples show that the regularity theory for this problem is actually a very, very delicate and intricate mathematical puzzle. So the first thing there is noticeable is that it is possible to build up fully nonlinear, uniformly elliptic operators for which solutions have unbounded Hessians. So in particular, it implies that solutions fail to be of class C11. Well, that's noticeable, but there's something even more striking, and the thing goes more or less like this. You fix your favorite number, tau, between 0 and 1, strictly, and then you build up, it's possible to build up an operator, f tau, let's call it f tau, right? There is lambda elliptic, whose solutions fail to be of class C1 tau. Right? Okay, but then you say, well, these guys are working with fully nonlinear operators. Maybe there are some things, some structures, something that we don't completely understand so far. Well, let's talk about linear operators, right? Very recently, Dong and Kim showed and built counterexamples in which linear elliptic operators with piecewise constant coefficients fail to have solutions in W2P. Right? And this is striking. For linear elliptic operators with piecewise constant coefficients, they are very common. If you're studying heat conduction in mixed materials, and you have, I don't know, intertwined boards of wood and iron, and you want to study heat conduction in this body, this is the kind of operator that governs the phenomena you're studying. So you're dealing with something that is pretty common, and and has a wide range of applications, but still it's possible to build an operator like this that fails to have W2P regularity. Okay. So not only the questions were set in the negative, but they were set in the negative in a very disturbing way. I mean, perhaps there are something behind this statement, f d2u equals 0, f d2u equals f, that we are not fully, completely understanding, right? Okay, so intuitively, the idea is that there are some special hidden structures here. And these special hidden structures, they hold the key to a more general or more stable regularity theory for fully nonlinear elliptic equations, right? So there is room for alternative methods. Since our classic methods are not actually seen, are not actually touching these structures, there is room for alternative methods and techniques that can be applied to touch these special structures in the statement, and then unveil some underlying general mechanisms that will allow us to recover regularity and to write and to obtain a corpus of results to some extent more general. It's this idea of an alternative method that takes us to the second part of my talk, that is about geometric tangential analysis. Right? The idea of the geometric tangential methods, geometric tangential analysis, is to build a toolbox that, on the one hand, puts your problem of interest. On the other hand, there is another problem, and this problem is something that you know, that you have information about. And then the idea is to approximate in some way, is to connect those things in some way that you can obtain information for your problem of interest, extracting this from the problem you know very well, right? So the connection between these things is a genuinely geometric structure and is called a path. At the core of this analysis is the idea of a path connecting your problem to a problem, an alternative one, a model problem, for which there is more information, and then you expect to extract information from your model problem back to your original problem of interest. There are various manners to design such a path, and today I'm talking about one called recession function. So the idea here will be to use a mechanism called recession function to connect our problem of interest to something else that may improve our knowledge about the structures we are concerned. Okay? So before we proceed, let me make a few comments about the idea of recession function, about the idea of geometric tangential methods, right? The idea of approximating objects you know and objects you're interested is not a completely new idea. It's an idea that is resembled by rationale of many individuals before. And one thing that is striking is that in the George's school, in particular in the George's theory of minimal surfaces, this idea of approximating objects and importing or somehow extracting information from something that you know to something that you're interested is very present. Right? Another example is Caffarelli's theory of free boundary problems. In this realm, perhaps also inspired by the George's school, what Caffarelli does is to approximate things, if two structures are closed in some particular sense, closed enough in some particular sense, then you can translate properties to some extent and obtain further information about the objects you're interested in. Right? Among others, for these ideas are permeating the analysis of PDEs, permeating other areas in geometry and this kind of thing. More recently, these ideas were put in a systematic way, were pursued in a systematic way, and I can mention, for example, recent developments due to Eduardo Teixeira and his collaborators, José Miguel Urbano from Universidade de Coimbra and Luis Silvestre from Chicago, in which in this literature, the idea of the geometric tangential analysis is made precise through a series of structures. Recession function is one of those. Okay. With that said, let me define a recession function. We have a fully nonlinear elliptic operator of this form. And then what we do is to denote by f star the following limit. F star of a matrix M is the limit of the operator f mu of M that is given by that. Right? So it's the limit as mu goes to 0, mu f, mu raised to minus 1, M. Okay? Intuitively, or from an heuristic point of view, f star accounts for the behavior of the operator f at the ends of the space of symmetric matrices, at infinity. This is the asymptotic approach. This is the asymptotic idea, right? You're investigating, you're importing information from the infinity of the space of symmetric matrices. Okay? So this nomenclature is borrowed from the realm of convex analysis, and if you're interested in this kind of thing, it's all over Rockefeller book and convex analysis. And for that reason, there's a wide range of applications in optimization problems. In particular, in some fields that are formalized mathematically by these techniques, we can mention, for instance, production theory in the realm of economics and continuum mechanics in physics, right? Okay, so let me show you a picture. This picture illustrates what I've been trying to tell you since the beginning of my talk, right? Suppose this is the manifold of all the lambda-lambda elliptic operators that you have, and you're interested in this point, your operator f, right? Then what do? What you do is to construct a path that is parametrized by this mu. When mu is 1, you're here. When mu is very small, as you leaves 1 and makes mu very small, you travel along this path, right? And when mu is very, very small, you're in the vicinity of f star. The idea is that f star has properties, important properties, and this will propagate in a vicinity of f star. And when you have mu very small, you're able to import to f mu, mu very small, these properties, and then carry them back. So in our case, if we assume that f star is, for instance, C11, right? This is, to some extent, to say that f has solutions w to infinity, right? When mu is very small, and we are very close here, we are not able to recover w to infinity, but we're able to recover a little bit less. So it's w to p for every p. Right? In the vicinity here, we recover w to p. And then, through this path, we're able to bring this information back to our original problem. Mu equals 1, there's f. Right? So this is the idea of the geometric tangential analysis. This is the idea of how the heuristics of how we want to proceed. Okay. So let me show you a few examples. So the first example is this Q momentum operator. So you fix an odd integer number, natural odd number, and then you consider this operator. It's an operator that depends on the matrix M through its eigenvalues, and is given by this sum. Right? This operator here, as you can see in this graph, the case of D equals 1 and Q equals 3, this operator, this is not convex, this is not concave, and in particular, this bump jeopardizes your hope to apply Evans Krylov, for instance, to obtain regularity for solutions of this guy here. But if you compute the recession function for this, you end up with the Laplacian. So the idea is you have something that is nonlinear, you apply your recession function, and you end up with your Laplacian operator. A similar thing happened with oscillatory operators, right? You have a perturbation of a sign of the eigenvalues, and this is the graph of this thing. You by no means have hope to apply classical results to this guy, but then you end up with a perturbation of the Laplacian operator. A third example, and this is a special example, not only because it's the special Lagrangian, but it's special in the sense that the special Lagrangian equation governed by this operator is important in differential geometry of minimal surfaces, area minimizing submanifolds, in the following sense. Geometric properties of the manifold are described or are proved and are obtained by establishing regularity of solutions to the special Lagrangian equation. So for that reason, this is a very important operator in the realm of differential geometry as well. This is not a convex thing. This is not a concave operator. We cannot apply usual techniques to this. But then we end up by applying a change of coordinates, a change of variables here. We end up with the Laplacian operator, again, as the recession function, right? So the idea is, of these examples is to give you a flavor of how this geometric tangential method can attack a variety of problems. Okay, let me now give you our main result. Our main result reads as follows. You have a fully nonlinear uniformly elliptic operator. P is greater than dimension, and U is a viscosity solution of this equation. Making an assumption on F star, namely F star has a priori C11 estimates, then the solution is in W2P locally and satisfies this a priori estimate. So the idea is that the only thing you need here is to impose on F star certain regularity, and through your recession function, you go to the infinity of the SD and recover not all this regularity, but is slightly less, and establish that solutions are W2P locally and satisfy this estimate. To prove this result, we have to combine two different sets of results. Right? So first, we consider some standard technical results in measure theory. So in particular, we want to study this quantity in terms of certain families of sets, in particular in terms of the measure of sets like this. We are interested in the measure of the sets where deviation is large. Right? Okay, so to prove W2P regularity for the solutions, we must investigate decay rates for the measure of those sets. That's the point where the geometric tangential analysis kicks in. Here, at least from an intuitive point of view, what you're saying is, if your Asian is growing, is too large, the C11 estimates for F star will make it go down because of the following. If your Asian is growing, the operator governing your PD is actually F star. Right? But F star has C11 estimates. So the Asian cannot grow too much. So it forces the Asian to go down. And then if it comes up again, then F star kicks in, forces it to come down. But this waving hands thing is not a proof. And we have to formalize this intuition in some way. The proper way to formalize this intuition is through an auxiliary result that we call an approximation lemma. This approximation lemma is actually the correct way to formalize this competing inequality that is set by the recession function. And then it builds up technical, more or less standard results in measure theory to yield the best decay rate we need to establish W2P regularity. How is our approximation lemma. The approximation lemma goes like this. We have for f mu of d2u equals f, and we assume the f in LP is small, and mu is as well a small number. Then we have a solution, h, to this equation, the homogeneous equation associated with the recession function. This function lies is in C11 in a smaller set, and it's close to u. This delta close as you want. And the thing here, the point here is that because we have this proximity, then we can attack a series of measure theoretical results that will ensure the proper decay rate for the measures of the sets where the Asian is big, where the Asian is large. Right? And once we have that, then it's standard to obtain W2P regularity. Okay, now we have our main result. We have an idea on how to establish, but it has a few consequences on the theory on the regularity theory for fully nonlinear elliptic PDEs. And this is what I'll present to you now. So the first thing that I want to tell you regards operators with variable coefficients. So the idea here is to extend our main result to this class of operators. Typically, we are considering this kind of object in this kind of equation in B1. And then, in accordance with Caffarelli's result from '89, one thing that we should introduce is a proximity measure. Right? And I want to stress one thing about this proximity measure. Here, this is defined in terms of the operator, right? So this is beta of f, and it's given by that, right? Okay, in this f appears here because I have more than one operator, right? I have f mu, and I have f star, and it's important to identify this oscillation in those terms. Our result about variable coefficients reads like this. We are concerned with this equation, and we assume the recession function is uniformly convex with respect to m. So what you're saying is that if you want to have some intuitive idea of what's happening, we are saying that outside of a large ball, the operator can be changed or modified to be convex. This is more or less the idea. In the infinity of the space of symmetric matrices, the operator can be modified to be convex with respect to m. Also, there are constants c, non-negative constants c and alpha, such that this condition is satisfied. Right? This condition is saying that the oscillation here has some C alpha regularity in Ln sense. But notice here we are talking about beta f star. Right? So if f star is uniformly convex with respect to m, and if this condition is satisfied, then u is in W2P, and this a priori estimate is verified as well. Okay. What's interesting about this result? This result extends our theorem to the case of variable coefficients, but even under previous development regarding variable coefficients, there is a novelty here. And the novelty is encoded, it's hidden. The novelty is a structure hidden in this beta f star. Why? We are not assuming the oscillation to be small at the operator level. We are assuming the oscillation to be small at the recession level. What does it mean? It means that if you have an operator with variable coefficients, let's say only measurable coefficients, if the recession function is such that this thing is satisfied, then you're in business. So the assumption here is much weaker than impose a condition on the oscillation at the operator level. Because the oscillation here at the recession level is always, at most, the oscillation at the operator level. It's always below. In particular, there are examples of operators, of fully nonlinear elliptic operators F with coefficients, only measurable coefficients, whose recession function has no coefficients. So this would be 0. Right? And there is another remark that I'd like to make about it. There's the following. This is some sort of C alpha regularity in LP sense. But if we assume this quantity here to be small in LP for appropriate P's, this machinery holds. Okay. This is expected to hold. Okay. So this is the first extension I plan to present. And the second one regards regularity in Bml spaces. So our main result under this additional assumption, the additional assumption that F is equal to F star outside of a large ball in SD, our main result builds upon previous developments in the literature to yield regularity of solutions in PBMO spaces. Okay? So the result reads more or less like this. Use a viscosity solution of this problem, and we assume the source to be PBMO for P above the dimension. Okay? Then the Asian is again PBMO locally, and this estimate is satisfied. Okay? There's here a remark, and it's quite an important thing. Then it's a simple thing, but it's important. If you recur to John Nirenberg inequality and proceeds with some very basic tricks, what you figured is that PBMO and QBMO for P and Q strictly between 1 and infinity are the same. And the norms in those spaces are proportional right? So what we are saying here is that although we are asking F to be PBMO for P greater than D, this P can be anything above 1 and strictly below infinity, right? So this is how our result, this is not an extension, but this is how our result reverberates in PBMO regularity. Finally, here, let me present a result about W2P density, the density of solutions, W2P solutions, in the class of viscosity solutions. So the result goes like this. F is again integrable in LP. The operator has now variable coefficients. It's an elliptic operator. And there is a viscosity solution of this problem, U, denoted by U. Right? So for every delta strictly positive, there exists a sequence of functions, Uj, j above 1. There is W2P locally, right, and belongs to this class, to the class of viscosity solutions of all the lambda minus delta, capital lambda plus delta, uniform elliptic fully nonlinear operators with source F. And what I'm saying here is that if you have your favorite fully nonlinear uniformly elliptic operator, right? Pick one, your favorite one. You wake up in the morning and say, this is my favorite fully nonlinear operator. I cannot tell the solutions to this operator are in W2P. But I can assure you that the solutions to your favorite operator can be approximated by W2P functions, and that's okay. But W2P functions that are in this class and are viscosity solutions to two elliptic equations with a slightly tilted ellipticity here. Okay. Oh, but delta is too much, so you can choose, well, it's for every delta, right? So you don't want to tilt so much your ellipticity constant. That's fine. You can put delta over 117, and it still works, and still you can approximate, right? So the idea here is that you can approximate the solution of any fully nonlinear uniformly elliptic equation by functions in W2P that are also in the class of viscosity solutions. And this leads me to two observations. And the first one of these observations is that we can somehow, based on this result, bypass the formalism, the viscosity solution formalism there is present in, for instance, the subconvolution or upper-lower epsilon envelopes when you need some regularizing argument. So you need an additional regularizing argument, and this is the mechanism that is out there for that. We can bypass this formalism if what you need is W2P regularity. Even more, we can say that if you are interested in a property that is closed under uniform limits, we may assume, without loss of generality, that solutions to this are local in W2P. Okay. So this is, if you're interested in establishing properties that are closed under uniform limits, the starting point now can be W2P. Okay. It leads me to my finish point, and I want to thank you for your attention.